Howdy folks, it's Mark McDonald with Home CSP here. Beautiful sunny, cold and windy day. As you may know, satellite dish actuators aren't as common as they used to be, and a lot of the linear actuators being sold now don't have pulse feedback systems. So this makes them really hard to adapt for digital solar tracking. It's still easy to use them for photovoltaic tracking, but astronomical tracking, what I call digital tracking, very hard to do with these systems. So an accelerometer is an ideal solution to this problem.
Alright, so here we've got a little accelerometer module mounted on this test stand I 3D printed. So this acts basically like a dip tilt axis. We can rotate about this axis, which we can change the tilt on. This is the tilt. This is what we call the dip. Tilt and dip. Okay, because it dips to the side, right? Dips to the side. Okay, so the accelerometer measures the angle, and it can. This is a 3-axis accelerometer, so we can measure both these angles. What we're going to call roll and pitch. Okay. So before we do that on our mount, where we would calibrate it to this middle position and 45 degrees to each side, we have to calibrate the accelerometer module itself, and for that we need it to be free mounted so we can rotate it to measure the minimum and maximum, i.e. +1 and -1 G on every axis for the X, Y, and Z. And you can see it's got the axes labeled there. Alright, so now I'm going to set up the mode on the motor mode on M1 for using an accelerometer. Alright, for a dip tilt axis. That's my plan. So I don't want to help. Yep. Okay, standard HP2 motor driver. Yes, we're going to go with that. So we have an option of gear or actuator arm. I'm just going to go ahead and go with gear for now. So we can choose polar, horizontal, azimuth, or a dip tilt system. So I'm going to say dip tilt, reset direction to the east. That's fine. So we can choose the pulse. Let's see, pulse, potentiometer, inclinometer, or accelerometer. I'm going to go with the accelerometer. I'm going to tell it we've got 3 axes on the accelerometer, and so the input is connected. It is connected to port 0 here. We've got the ground, then the X, Y. Here's our 5-volt we're pulling off. We skip a port there, and here's our Y, and here's our Z from the accelerometer. So those will all be consecutive from A0, A1, A2. So I'm going to select OK. Ask if this is being used to measure pitch, as well as pitch would be on the secondary axis. Primary axis we're measuring roll, and yes, we're going to measure both pitch and roll with this sensor. And we like to calibrate it now. I'm going to say no, just so I can show you how to do it separately. Alright, so now we're going to do the calibrate procedure for the accelerometer. So that's only available on the motor menu for M1 or M2 when we've selected accelerometer or inclinometer for our feedback, position feedback. So we'll select cal now. So calibrate device. Are we ready? Yes, I'm ready. Okay, first we're going for X minus 1G sensitivity here. So it's displaying the current minimum that it's got. And I'm going to rotate the device. So here's the device, and you can see the X vector there pointing to the right. So I'm going to orient that down, and as I do that, we'll see this value get smaller and smaller. So it stores the minimum value, and looks like 204 is the minimum. Now if I just happen to I'm just going to shake the device here. So now I've got this false minimum. Well, I can press the up button on the keypad here, and you see how it reset it to the current value that it's reading. So this lets me kind of reset. So I'll go again here. I'm going to get the 204, kind of move it back to a little bit of an angle so I don't jostle it. Now I'm going to press OK. Okay, and now I'm ready to do the maximum. So just like this, except this time I'm going to rotate it the other way around so that x-axis arrow is pointing up. And yes, sirree, it does look like I've got a false reading here. So now this time I'm going to press the down arrow, and I reset that. So now I'm gently rotating. Yeah, looks like, okay, so 303 is the maximum there. Okay, so that takes care of X. Now we're going to do Y. Same thing. This time I'm doing the Y arrow down. At 203. So I'm going to do the Y value up here. Maximum value. I think that probably needs a little reset there. Come on. Well, you got to be really careful when doing this so you don't jostle it. Okay, yeah, 303. It looks like 303. 304, we'll go with that. Okay, now we do 0, or minimum for the Z here, I mean. So I'm just holding it by hand here. Rotate it around. That looks like 210 would be fine there. And now Z max. The other way. Shook it around too much. Reset there. Okay. 13 value. Alright, and now lastly we want it on a flat level surface. And so I've got this mount here on the bottom, so I'm just going to overhang it on the edge here, hold it flat and still, and then I'm going to start it here. And that's going to be really hard to do with here. Good. Okay. And so say start, and it basically just does a countdown, and it's making continuous readings during this period and averaging that all out for what it's going to call this 0 degree. So that helps compensate for any mechanical misalignment on the PCB and in our sensor housing. Alright, so now that it's got that, finally we're left here, we're two more things. First we're going to do the minimum alarm and then we're going to do the maximum alarm. So here we see that our minimum reading of their X, Y, Z values was 203. So by default, it basically divide that in half, and if we get anything that's below 101 or below, it's going to call that an alarm. So that sounds good to me. And now we get to set the max alarm. So yeah, that's pretty high. We want it a bit low, so I just kept bumping it up, and it circled it around to what our maximum was, and I'm just going to bump that up to like let me say 400. And if the signal was ever higher than this, then I would suspect that something's just wrong with the wiring or the sensor itself, and so that would we wouldn't use the accelerometer information. We would just hold still and report the error. So set that alarm value, and that takes care of the calibration. So that's how you do the accelerometer calibration. Now we still need to mount our sensor on our mount, right? Okay, now it's mounted on the mount. Now we need to teach it where, and actually just totally define, you know, okay, this is 180 facing south, this is 45 towards the east, this is 45 towards the west, or would it be, right? And likewise with the elevation. So we still have to do that, and that's all done with the align command. And we would also want to use the limit command to define our maximum tilt to each side for the M1, and our maximum and minimum elevation for M2. So that's a quick overview of setting up the Mega Tracker with an accelerometer sensor.
So you might have noticed when we were doing the accelerometer calibration that our maximum values were fairly low. So we've got a solution for this. So first of all, let's do a quick review of how the analog to digital converter works in practice. So the Arduino Mega is equipped with a 10-bit analog digital converter. This gives 2 to the 10th power steps of resolution, which equals 1024. So this means our values range from 0 to 1023 maximum. So if we are to graph this, we can see how basically it's a linear relationship. As the input voltage changes, we get a bigger number till we reach our maximum, and this is our scale from 0 to whatever the analog reference is. So the default analog reference is 5 volts. Now this means that the minimum voltage change that the ADC can measure is going to be equal to 5 volts divided by 1023, which equals approximately 4.89 millivolts. Now, fortunately, we can change what the analog reference is. And in fact, the microprocessor has a variety of analog voltage levels that can be set internally without requiring any external modification. So the most useful one for us is going to be the internal 2.56 voltage reference. Now using this means that the minimum voltage change that can now be measured is 2.6 divided by 1023, which equals approximately 2.5 millivolts. So that basically effectively doubles our resolution with our measurement of analog voltage signals. Now, whether or not we can use this feature depends on any other devices that might also be using the analog to digital conversion. So we can't go changing the analog digital reference between readings on different ports. So all ports have to share the same analog reference voltage. So yeah. All right. So now let's have a look at how we change the analog voltage reference on the Mega Tracker.
Okay, so we're going to access the analog reference settings now. That's under Setup and GPIO, General Purpose Input Output. Right there at the top there, Aref. We select Aref. And here are the available choices. The default, which is of course 5 volt. The internal 2.56 volt. It's also an internal 1.1 volt, or we can select an external voltage reference. So that's kind of an advanced subject and probably worthy of its own little special video should the need be. Anyway, by selecting 2.56 to 2V56, now what would previously have measured at 512 is now at the maximum scale. So previously our alarm was at 400, and so now that equivalent reading would be 800, or what the plus 1G was around 300. It was a little bit more, so let's call it 600 plus. Maybe it's 610 or so, 620 for a 1G reading. So anyway, of course, now that we changed the analog reference, we also need to recalibrate the accelerometer so that we get the correct values for the new analog reference and get those stored in the configuration. Okay, now, so I've recalibrated the accelerometer with the new analog reference, and so this is the default idle screen, the information that's displayed. Not particularly useful for what we want right now, so I'm going to go to the show command, what I want to be shown, and I'm going to go ahead here, select this. Let's see, make this the pitch. We'll make the top one the roll. All right. All right, so now we are displaying values for the angle being measured. So we've got a 14 pitch and just a little bit of tilt, right? So if you look here, you can see there's just a little bit of roll to the side, and it's about a 14.5 degrees from vertical, right? So now I'll move this to, it's about a 45-degree angle, and look at that, 46-degree angle, and we're still 180, basically flat here. I'm going to rotate this, and see that the pitch did not change, but our roll is now approximately 130 degrees. So It's just updating I forget, once or maybe twice a second here. While it's idle, that updates more frequently when it's doing a motor movement. But the value is also filtered, and so that's why it sort of slowly changes here till it reaches the little happy point. And that filtering causes just a little bit of rounding error, because it's we're getting numbers that are higher. You know, we've got more resolution in our numbers than in our conversion value here. So, but with the 2.56 analog reference now, we've got just a little bit better than 1 degree resolution on average across the range of motion. Anyway, that shows how easy it is. I hope that was easy to set up an accelerometer, work with the Mega Tracker, and this can replace pulse feedback and other position feedback systems that you might have used in the past. So I hope you found this interesting. Thanks for watching.